Okay, so we're going to look at maximum and minimum points or turning points. So we've seen these before. When we looked at functions, we would have looked at our turning points, and we said our turning points were the points where the function turns. So if you're following the graph of the function, or if you're following the path of the function, I suppose, we kind of use that example of maybe somebody cycling. If they were cycling down, the turning point is where they would have to kind of turn their bike around and start turning the other way. So we know how to find them by looking at the graph, but what we're going to do now is try and use calculus to help us find these turning points without having to use the graph. So it's going to speed things up a little bit for us, and particularly will help us then with some real world examples. So looking first of all at what we have here. At a turning point, a maximum or a minimum turning point, doesn't matter which, dy dx is equal to 0. So we're remembering again, obviously dy dx is our first derivative, so sometimes called that f dash x or f prime x. It's our first derivative. So at a turning point, this first derivative is equal to 0. And we can think about what that means if we take maybe a quadratic example. So say we were to draw a quadratic graph over here on the side, and picking out our turning point or a minimum point, we can see it's down here in the middle, down in the center. And we know from before that dy dx is the slope of the tangent to the curve at a particular point. So at this point, at this minimum point, the tangent would look something like this. And a line like that goes straight across, would have a slope of 0, because it is neither increasing nor decreasing. It's not going up the way, it's not going down the way. The slope is just 0. It doesn't change, none of that. Remembering as well that dy dx is the change in the y value as the x value changes, and that line isn't going to change at all. It's just going to stay flat, it's going to stay at a slope of 0. So that's where it comes from, I suppose, if we link that idea of understanding why dy dx is equal to 0. But it's also just something that we're going to have to really remember. So at a turning point, and remembering that that's a maximum or a minimum point, at this turning point, dy dx is equal to 0. And another point, I suppose, as well, that a turning point is your x and y coordinates. So for a turning point, we give the full coordinates. If we're asked for maybe a maximum or a minimum value, that's going to be the y value at that point. And we might have questions where we are asked for that max and min value, or maybe asked for the x coordinate that gives us a maximum value. So it's just being careful about what you're being asked and making sure that you're giving that in your answer. And another point as well is that these turning points are sometimes called stationary points. Okay, so again, a few different names for the same kind of thing. So maximum and minimum are examples of turning points and also called stationary points. So if we're asked to find stationary points, or if we're asked to find turning points, we know what we're looking for. So let's see what this looks like in action. We have a graph here of f of x, which is x squared minus 2x minus 5 over on the right hand side. And the first step is we're asked to use the graph to write down the coordinates of the minimum turning point. So we go to our minimum point, we can see it down the bottom here. So in the center, down at the lowest point that the graph reaches, so I'll colour it in with the blue here. And our minimum turning point is going to be minus 1, or sorry, not minus 1, just 1 minus 6. So 1 minus 6 is our minimum turning point. And again, we can see that idea I was talking about of if you were maybe cycling along the path of this here and you're cycling down, you're following down, this is the point where you would have to start maybe turning the wheels to go back up the way. So now we have to use calculus to verify our answer. So first of all, let's just make note that we remember at a turning point, dy dx is going to be equal to 0. So first of all, we need to find dy dx. Now in this question, we can see that we don't actually have y, we have f of x. So let's keep our notation consistent. So instead of saying dy dx, maybe we'll say f dash x, means the same thing, 2x minus 2. And we are going to set that equal to 0. Okay, we're going to say that's now equal to 0. So now we're going to solve for x. So 2x is equal to 2, x is equal to 1. Okay, so that's our first part, x is equal to 1. Now we don't stop there because we know that we're looking for coordinates. We're looking for the coordinates of the turning point. To find the coordinates, we're going to have to sub back in. So we're going to look for f of 1, which is 1 squared minus 2 by 1 minus 5, 1 minus 2 minus 5. Okay, so let's have a look at that then. So then that gives us an answer of minus 6, which is what we had already. So our coordinates are 1 minus 6, matching the answer that we had when we looked at the graph. So that's what we want, obviously. So we can see that with our calculus there, we didn't even need the graph of the function to still find these minimum points, to find this minimum turning point. But important that we go back and look for the y value that goes with it if we're asked for coordinates. So again, it's just making sure we know what we're being asked. The next question here, following the same idea, but this time we don't have a graph, so we don't have any choice in how we find it. And we're asked to find the local maximum and the local minimum of the curve. If we take a second maybe just to look at this curve has an x cubed. And we should know that an x cubed gives us a cubic graph, which looks something like what we have here on the right hand side. So a cubic graph will look something like that. It goes up, it goes down, and it comes back up. And with a cubic graph, we can see that there's a point here and a point here that we would consider to be a local maximum and a local minimum. And the reason we use those words local is that these points are the maximum and minimum point around a certain area. So obviously, because our graph continues on forever, it will get to higher points than that one that I've marked in blue. But for this small range, this small snapshot that we've taken, this is the highest point that it's going to reach. And the same with that minimum point. The graph has been at smaller values, but for this range, that is our local minimum value. Okay, and again, it's the idea of thinking these are turning points. So the local maximum, but those are the maximum turning points. Okay, so it's linking all these things together. But in terms of how we're going to tackle the question, we're going to approach it the same way. We know dy dx is equal to 0. So let's find dy dx. And we get 3x squared minus 18x plus 15. Okay, we're going to set that equal to 0. We should see at this point that that is a quadratic. Okay, so we should see that's a quadratic. We should remember to solve a quadratic. We have a few different ways. What I'm going to do this time, just to give us a few variations, we're going to look at the quadratic formula. Because the quadratic formula will work for any quadratic that we have. If we want to solve a quadratic, we can always use the quadratic formula. And it can be one that if you get used to using it, it can be quite easy then to work with. And you can be confident in working with it. So first of all, we just have to line up our A, our B, and our C. And then we can sub them in. So the minus 18 becomes a plus 18. We have minus 18 squared here, minus 4 by 3 by 15. Okay, and that is all over 2 by 3. Okay, so let's see next of all. So 18 plus or minus, then we need 18 squared. Okay, so 18 plus or minus, and we're going to get 18 squared. So let's just quickly get that calculation for ourselves, 324. And then 4 by 3 by 15 gives us 180. And that is all over 6. And again, we're just following this through. At this point, you could put this straight into your calculator if you wanted to. I'm just trying to show as many steps as I can, particularly if I'm trying to show an examiner that I know what I'm doing. So again, keeping this going, 18 plus or minus 12 all over 6, which means that x is equal to 3 plus or minus 2. And then we take these two values. So x is either equal to 3 plus 2 or x is equal to 3 minus 2. So x is equal to 5 or x is equal to 1. Okay, remembering again, same as with the last example, that we're not finished there. We're looking for coordinates. So we have to find the y values. So to find y, so for x is equal to 5, we're going to take the original function again. So y is equal to, so let's make sure, 5 cubed minus 9 by 5 squared minus or plus 15 by 5 plus 2. And we'll do the same with x is equal to 1. So that's going to be 1 cubed minus 9 by 1 squared plus 15 by 1 plus 2. And again, just following this through, 5 cubed is going to be 125 minus 9 by 5 squared. So again, these are the sort of things that we can work out on our calculator. 225 plus 15 by 5 is 75 plus 2, so 125, and that's going to give us minus 23. And on this side here, 1 minus 9 plus 15 plus 2, and that's going to give us 9. Okay, so looking at this point now, we need to just write down our coordinates. So our two turning points are 5 minus 23 and 1, 9. Let me just move all this down a little bit, so that would give ourselves a little bit more space just to finish this one out. And we have to decide now which is going to be the maximum and which is going to be the minimum. So in order to decide that, we're going to look at the two y values, and we can see that for this one on the left hand side, the y value is smaller. And what that indicates to us is that this one is going to be our minimum, and this one is going to be our maximum. Okay, and that keeps it nice and clear for us there, that we can see exactly which is which. Okay, so we've seen that we can find our y values by subbing back in. We can use those y values to find whether it's a maximum or a minimum, but we also have a clearer way, or a more kind of concrete way of checking whether we have a maximum or a minimum value. And this can be particularly useful, I suppose, if we're looking at a curve that we're just not 100% sure what the shape of that curve is going to be. And to do that, we're going to use the second derivative. So obviously our second derivative is going to be related to our first derivative. So we're remembering that dy dx was our first derivative. So to get our second derivative, we're going to differentiate this again. Okay, and when you're differentiating, you can think of y as the function that we start with. Okay, so y is our function that we start with here. And our dy dx then, or this d dx, is the differentiation that we're applying to that. Okay, so when we come to do our second derivative, we're applying that differentiation a second time. And that's where we get our notation here of this d2y dx squared. That's where that notation comes from. So we're applying this d dx, this differentiation, to y for a second time. And obviously our alternative notation there is the f dash dash x, or f double prime x. Again, whatever we like to call it. So we're going to see how this works in actuality. So first of all, we're just going to look at finding the second derivative. And as we've said there, to find the second derivative, we first find the first derivative, and then we're going to differentiate it again. So let's have a look at how that works. So for this first question, if y is equal to this, we're going to find dy dx and then d2y dx squared. So the first derivative and then the second derivative. So let's find the first derivative. Again, the same rule, we multiply by the power, we reduce the power by 1. So 3x squared becomes 6x, minus 5x becomes minus 5. Then to find our second derivative, we look at the first derivative. So we're looking back at this one, and we're going to apply our rule again. So multiply by the power, reduce the power by 1. So the 6x becomes 6, the 5 becomes 0. And that's it. That's our second derivative found. So applying just the same rules. For this second example, let's first of all find f dash x or f prime x. Same idea, that the x cubed becomes 3x squared. The 2x squared becomes 4x. The 4x becomes just 4. Then to find our second derivative, we're going to look back again at our first derivative. The 3x squared becomes 6x. The minus 4x becomes minus 4. So we can see here that the second derivative still has that x value in it. So obviously our second derivative is still dependent on x for this function. And we've actually been asked to find f dash dash 2 minus 2. So the second derivative when x is equal to minus 2. So we just sub in for x, and we get minus 12 minus 4, which gives us minus 16. Okay, so our second derivative when x is equal to minus 2 is minus 16. And that's our answer for that part of the question. So we can see they're finding the second derivative, we're applying the same rules, we're doing it exactly the same way that we find our first derivative, we're just differentiating the first derivative instead of differentiating the original function. So the key things are to make sure that you're looking at the right function when you go to look for your second derivative, and that you keep your notation correct. So when we have y as our original function, if we differentiate that, we have to make sure that we do use that word dy dx or the f dash x. We can't continue to call it y because it's no longer y. It's now a different function. It's the slope function for that particular equation. And the same thing goes with our second derivative then. When we find our second derivative, we have to make sure we use that new notation again, the d2y dx squared. So it's just being consistent with what we're writing here. Okay, so we might ask ourselves, why do we want to do this? Why do we want to find this second derivative, or what's the use in finding this? And that comes in with what we call the nature of the turning points. And by talking about nature of turning points, we're talking about that maximum or minimum value. So for a turning point, I've just called it A here, it doesn't really matter. But for a turning point, we know that dy dx is equal to 0. And we said that in the start of this section. But what we also now are going to make note of is that at a turning point, dy dx is equal to 0, yes. And if the second derivative is less than 0, then we have a maximum turning point. If the second derivative is greater than 0, then we have a minimum turning point. So again, a little bit kind of counterintuitive, but just something we're going to have to really remember. Second derivative less than 0, it's a maximum. Second derivative is greater than 0, it's a minimum turning point. The minimum. And this applies to our turning points when dy dx is equal to 0. So we know that for it to be a turning point, dy dx has to be equal to 0 at that point. Okay, so it may be a case that when we come to the second derivative, we have to sub in that value of x, or it may just be that the second derivative is a constant that is either less than 0 or greater than 0. So let's see this in action. Let's look at an example. So we're looking for, if we write down what we're looking for coordinates of the turning points. So coordinates when dy dx is equal to 0, and then we want to get max and min. We want to say whether it's a max and a minimum. Now, why am I saying dy dx is equal to 0? Well, we're told turning points. We should know that at a turning point, dy dx is equal to 0. As I've said there, we're looking for coordinates, and that we're going to use the second derivative test. So let's just first of all just find our dy dx. So the same way we've always done it, we're going to take our function, the x cubed becomes 3x squared, the minus 3x squared becomes minus 6x, and the 5 just goes to 0. So looking at this here now, we should recognize if we want to solve for x, and let me see, I should write this equal to 0 first. If we want to solve for x, we're going to have to factorize. So let's just make a note of that. We need to factorize. And why do we need to factorize? Well, because we can see for our equation here that we have two terms that both have x's. One of the terms has a higher power of x than the other, so one has an x squared, one has an x. So in order to solve for x, we're going to have to factorize and end up with two factors that we can put equal to 0 and then solve for. So if we're factorizing, we need to know our different types. I generally tell people we'll start with quadratic, we'll then move down to maybe difference of two squares, then we'll try grouping, and then we'll try highest common factor. We're going to work through it in this order. So starting with quadratics, this wouldn't be considered a quadratic because it only has two terms. So we're going to say it's not a quadratic, not in the traditional sense that we'd be used to. If we look at difference of two squares, it's not going to fall under that category either. Okay, then looking at grouping, we don't have enough terms for it to be grouping. So all we can do is look at highest common factor. So we need to factorize the highest common factor that they have. So we're looking for the biggest thing that divides into both terms, and that's going to be 3x. For the 3x squared, that'll leave me with an x, and for the 6x, that'll leave me with a 2. Once I get to this point, I have two factors. The first factor is 3x. The second factor is this x minus 2. And what we want to do at this point is we take our two factors, our 3x and our x minus 2, and we set them both equal to 0 separately. So the 3x first of all over here, and the x minus 2. We would be used to maybe doing a quadratic and seeing something like maybe an x minus 3 and an x minus 4 is equal to 0, and then saying x minus 3 is equal to 0, x minus 4 is equal to 0. And what we're doing there is the same thing. We have two factors, so we take each of them and we put each of them equal to 0. Although in this question, our factors look a little different. So one of them has the nice brackets we're used to, one of them is just 3x on its own. Still okay, we do the same thing. We take the 3x, we put it equal to 0, we take the x minus 2, we put it equal to 0. Following that on, we get x is equal to 0, that's by dividing by 3, and here we get x is equal to 2. Okay, so we're going to use the second derivative test to test whether each turning point is a maximum or a minimum one. So let's maybe do that now. So d2y dx squared. So we need to find our second derivative first. So the 3x squared is going to become a 6x. The minus 6x just becomes 6. And that is all coming from me differentiating this first derivative. So we're going to try our different values of x. So for x is equal to 0, we get an answer of minus 6, and for x is equal to 2, we get an answer of plus 6. This is less than 0, which means that that one is going to be related to our maximum. The plus 6 obviously is greater than 0, and that's going to be related to our minimum turning point. So this is going to be part of our maximum turning point, and this is going to be part of our minimum turning point. Now we do know from what we've said at the start, we're looking for coordinates. Okay, not just an x value, we need the coordinates of our turning points. So to find those out, we're going to have to look for the y values. So going back to our function from the start, we can just maybe write it out again for ourselves. So y is equal to x cubed minus 3x squared plus 5. So first of all, let's do when x is equal to, so I'm just going to move this down a little further, just to give myself more space. So first of all, let's do x is equal to 0 over here. So y is equal to 0 cubed minus 3 by 0 squared plus 5. So that's going to be equal to 5. So my coordinate is 0, 5. And we know that that is the maximum. Or if we like, we can keep the same words, the local maximum. Okay, so it doesn't matter, we can say maximum or local maximum, doesn't matter. But it's a maximum turning point. It's a maximum turning point. Okay, and where do we come to that conclusion from? Well, we saw here that it was a maximum turning point, so we can keep this up here then. Okay, so linking those two ideas together. On the other side, we can do when x is equal to 2. We can find our y value, 2 cubed minus 3 by 2 squared plus 5. Following that through, 2 cubed is 8, is minus 12 plus 5. And we get an answer of 1. Okay, so our coordinate is going to be 2, 1, and we know that that is a minimum turning point. This TP is just turning point. So that is our minimum turning point. And again, linking that to our second derivative test that we did here. And we can see if we look at the points, we can see that 0, 5 is obviously going to be higher than 2, 1 in terms of where on our graph it would go. So we would be able to tell from the coordinates that 0, 5 would be the maximum as opposed to 2, 1, which must then be the minimum because they're both the turning points of the curve. But the second derivative test just allows us to be sure. And you can see there, it allows us to check even before we found the y values, whether it's a maximum or a minimum. So I'm going to skip over that little example here, and I'm going to just go on to our sketching our graphs, because we're going to do another go at that second derivative with this example. And in terms of sketching graphs, we've looked at plotting graphs quite particularly and quite exactly and accurately is the word, I suppose. So what we're going to look at now is how we can draw a sketch of a graph without having to draw up that table and plot out our coordinates accurately. We can use calculus, we can use all these things that we've learned in calculus and in functions, and we can use that to help us just understand and to draw a fairly accurate sketch. So recalling first of all that f of x is equal to 0 on the x-axis, and these are our roots. So the roots are where your graph crosses the x-axis, and that's when y is equal to 0. So what I've said here is we can use information from calculus to help draw a sketch of the graph. But we need to find certain key points. So the first one would be maybe the roots. Then we could look at the maximum and minimum turning points, and the y-intercept would be another one to look for. And something I'm going to add in as well would be, because it comes up in quite a few questions, would be the endpoints. So often we'll be asked to maybe sketch the graph within a certain range, so we might want to find the endpoints. And I will say we won't always find all of these points. We won't always find all of these key points, but if we find, obviously the more of them that we do find, the more accurate our sketch is going to be. But we'll look at this question here and we'll see how it kind of leads us through to find the sketch of the graph. So first of all, we're asked to find the maximum and minimum turning points of f of x is equal to x cubed minus 3x plus 2. So first of all, let's find dy dx. So dy dx is 3x squared minus 3. Okay, 3x squared minus 3. We need to set that equal to 0. Once again, we're looking at this question, we're thinking of our types of factorizing. We're saying it's not quadratics. It is not difference of two squares. It is not grouping, so all we can do is highest common factor. The biggest factor I could take out here would be a 3. So I can take out the 3, or I can divide across by 3. Because it's just a number, I can divide across by that number, and that's fine as well. So x minus 1 is equal to 0. Now x squared minus 1, it looks more like another type of question, and this is an example of a difference of two squares. So to factorize, we get x minus 1, we get x plus 1, all equal to 0. Okay, so then we have that x is equal to 1 and x is equal to minus 1. To find out whether they are maximum or minimum turning points, we can use our second derivative, which works out to be 6x. Okay, so so at x is equal to 1, we get an answer of 6. This is greater than 0, so that suggests minimum. At 6 multiplied by minus 1, we get minus 6. That is less than 0, and that gives us a maximum turning point. Interesting that we just had both answers be 6 on the previous question as well. Just coincidence. So at x is equal to 1, we have a minimum turning point. At x is equal to minus 1, we have a maximum turning point. Just using our second derivative test there to the side. So we've been asked to find turning points, so we should remember that if we're asked to find turning points, we're looking for coordinates. So we need to find coordinates. So we know y is equal to, or f of x, sorry, and I should really be consistent with my notation here, so maybe instead of dy dx we'll say f dash x, and instead of our second derivative let's use that notation for the second derivative with a function, which is f double dash x, or 2 dash dash, whatever you like. So let's find now f of 1 is going to be 1 cubed minus 3 by 1 plus 2, which gives us 1 minus 3 plus 2, and that's going to just be 0. Then if we look for f of minus 1, we're going to get minus 1 cubed. We're going to have to watch out for that one. Minus 3 by minus 1 plus 2. Minus 1 cubed is minus 1. This is plus 3. This is plus 2. So that gives us 4. Okay, so our first turning point is 1, 0. Our second turning point is minus 1, 4. Okay, so let me see. I'm going to move down my axes there a little bit because we have a bit more to find out. So first of all, we found our two turning points. Okay, 1, 0, minus 1, 4. We had already decided that minus 1 was our maximum turning point. Our maximum turning point was at x is equal to minus 1. Our minimum turning point was at x is equal to 1. And we can see from the coordinates that we are correct. That this is going to be our minimum one and this is going to be our maximum one. So that's going to be important when we come to draw our sketch. That's part A. Part B says to show that it crosses the x-axis at the point minus 2, 0. So to show that it crosses the x-axis at this point, we need f of x to be equal to 0. So we want to show f of minus 2 is equal to 0. And we put a little question mark because that's our goal. So we want to see. So f of minus 2 is minus 2 cubed minus 3 by minus 2 plus 2. Minus 2 cubed gives me minus 8. This is plus 6. This is plus 2. And that is equal to 0. Okay, so what does that mean for us? That means minus 2, 0 is a root. Okay, minus 2, 0 is a root of our function. Part C says find the point where the graph crosses the y-axis. So let's make a note for ourselves here. When it crosses the y-axis, x is equal to 0. So we're looking for f of 0 for part C. So again, I'm just going to move these axes down a little bit. So for part C, we are looking for f of 0. So 0 cubed minus 3 by 0 plus 2, and that's going to be equal to 2. So 0, 2 is what we call the y-intercept. Okay, it's the point where it crosses the y-axis. So 2 is your y-intercept. That 0, 2 is where we're going to look at for crossing the y-axis. Okay, now we're told to use this information, sketch the graph of f of x. So let's see how we can use those points in order to sketch this graph. So I'm just going to make sure my axes here in the middle are just centered on those lines. And I'm maybe going to take each of these points being, I'm going to take 2 squares maybe as being 1, just to give me room to work with. So minus 1, and I'm keeping my axes consistent along this x-axis, keeping my spaces consistent. In terms of the y-axis, I can just go up maybe in 1s because I'm conscious that there might be some points where I have to go up fairly high, so I don't want to leave myself short of space if that's the case. Minus 5. Okay, so let's just look at first of all the few points that we have. So we might decide to look at the roots first. So we know from this point over here that minus 2, 0 is a root. And what that means is that's a point where our graph crosses the x-axis. So at minus 2, 0, we can draw this point in. And let's maybe just make a note beside here. So we'll use that red dot just to make sure we can line up these points. Next, we're going to look at our y-intercept, or where we cross the y-axis, and that was the point 0, 2. So again, I'll make a little dot here, and I'll just line it up here. Okay, now we have to look at my maximum and my minimum points. Okay, so first of all, we have 1, 0 is my minimum point. So 1, 0, that's going to be here. And we know that that's a turning point. And then minus 1, 4 is another point here. So that's going to be here. Okay, so we're getting a picture of the graph here. We know that these two pink ones, okay, the two pink dots here, those are turning points. My maximum and minimum, we need to remember that those are turning points, and those were what we were talking about earlier at the very start with your bicycle. That's where your graph's going to turn. Okay, so we have to make sure that at those points on our graph, in our sketch, that our graph does turn at those points. So we're going to start here at this minus 2, and we're going to work our way up to this first turning point. This is our maximum turning point at x is equal to minus 1. Once we've reached that point, we're going to turn. We're going to go through the y-axis at the point that we've already marked, and we're going to come down to x is equal to 1. This is another turning point. So at this point, I know, okay, well now I need to turn and go back. So I'm going to go on up. I'm going to continue that way. What we can do over here as well is maybe just continue our graph a little bit this direction as well. And that's our sketch of the graph. Using the points that we found out, we found our maximum turning points. We know that the graph needs to turn at those points. The y-intercept told us where we're crossing the y-axis. The x-intercept, if you like, or the roots told us where we're crossing the x-axis. And we might have a case where we're maybe have to find more of the roots, which can be a little more difficult. A lot of the time they might give us one root, which helps us work with it. And then we might have a situation like this where we have maybe a kind of repeated root at x is equal to 1, which we looked at before. That's what it means for it to sit at that point. But those are the main things we need to know about our maximum and our minimum and our turning points. Okay, and that idea of our second derivative test, and we've seen then in this example how we can then use that a little bit further.